So today we're going to be talking about some basics of oscillations and simple harmonic motion. So the most common type of oscillation or simple harmonic motion is about a spring with a mass attached to it and it's stretched. So we have a spring attached to an immovable wall like this. And there's going to be a mass at the end of it. Presume the spring is like displaced an x distance from its resting position, so there's energy stored, elastic potential energy. So you know the force acting on the mass is just going to be negative kx, right? And you know also by Newton's second law, F is just equal to ma. And you also know that acceleration is just the second derivative of displacement. Now plugging this back here, you get an equation. Negative kx is just equal to mass times d squared x over dt squared. Right, now we rearrange it, so now we move these, so we get m d squared x over dt squared plus kx is equal to 0. Now we divide m from both sides, so we get d squared x over dt squared plus k over m x equal to 0. Now we're going to solve this equation for x. So the math here is pretty complicated. It's like university level, so we don't need it for high school physics. But I'll make a video after this if you guys want to. So the math here is pretty complicated. It's university level math. So like I'll make a video later if you guys want to see how you actually solve this equation. But here I'm just gonna put the solution here. So you just set random variable omega squared equal to k over m. So we get equation d squared x over dt squared plus omega squared x equal to 0. Now solving this equation, you get x as a function of t. It's just going to be equal to a, which is a constant, sine omega t plus phi. Now if you want to check if this is right, you can plug it in back to the original equation and you see that indeed it will become 0. So this is the equation for displacement in a spring. So also know omega is the angular frequency, right? So we know angular frequency is just 2 pi over period. So rearranging this, we get t is equal to 2 pi over omega, which is effectively, we know omega up here, omega squared is k over m, right? So dividing by omega, you get the period is just 2 pi square root, you flip these, so m over k. And this is the period of a spring. So now we have an equation for displacement. We can just derive this to find velocity. So we get velocity time is equal to a omega cosine omega t plus phi. This is just basic chain rule. So we see this, right? We can square both sides. We get x squared. Let's just neglect the t. We know it's a function of time, so we just leave this out for the sake of simplicity. A squared sine squared omega t plus phi. Also know v squared is just going to be a squared omega squared and cosine squared omega t plus phi. So now we add these together, but first we divide a squared from both sides and a squared omega squared. So you get x squared a squared plus v squared divided by a squared and omega squared. It's just going to be equal to 1, because you see if you divide both sides by these, right, you can get sine squared omega t plus phi plus cosine squared omega t plus phi, which is equal to 1 by our trig identities. So now we can isolate for v. So first multiply both sides by amplitude, which is a squared, so we get x squared plus v squared over omega squared equal to a squared. Now we just subtract x squared from both sides and multiply by omega squared and then take the square root. So we get v is just equal to first a squared minus x squared. Now multiply by omega squared, then take square root. Don't forget the plus and minus. Now we can just take the omega squared out. So we get velocity is just equal to plus minus omega a squared minus x squared. Now we can also derive velocity to get acceleration. So we get acceleration, which is going to be equal to negative a omega squared sine omega t plus phi. Now we can see, okay, just take out a and 1 factor of omega squared. Now we can see this is very similar to our equation for x of time. Now we can see this is very similar to our equation for displacement, which is a sine omega t plus phi. So we can just take out factor of negative omega squared, and we get a sine omega t plus phi, which is exactly our previous equation. So we can write acceleration. A is just negative omega squared times displacement. So the last essential formula you will need for a spring is the total energy of the system. So we know the total energy is just going to be equal to the speed the mass is moving at, so just first 1/2 mv squared, plus the elastic potential energy of the spring, so just plus 1/2 kx squared. Now we know from our equation earlier that velocity is just plus minus omega square root of a squared minus x squared. So we can plug this back here into this velocity, so we get this equal to 1/2 m omega squared a squared minus x squared inside brackets, plus 1/2 kx squared. Now we can write omega squared as k over m, right? So we can replace this, and you see the m's cancel out, so we get 1/2 k a squared minus x squared plus 1/2 kx squared. Now we can expand this, it becomes pretty obvious, you can cancel them out. So you get 1/2 k a squared minus 1/2 kx squared plus 1/2 kx squared. So we can see these terms cancel out, so just get 1/2 ka squared. But now you can also express k in terms of omega and mass by this equation. So we get it's also equal to 1/2 a squared, move mass there, so it's omega squared and mass. These are the equations for the total energy of a spring. Now, if you come so far into the video, I assume that you're very interested in physics, because, you know, like, I suck at teaching, so like most people wouldn't watch the video this far. So as a reward, I'll make you guys derive a formula for oscillation yourself. So, you know, a pendulum is also a form of oscillation. So let's draw a pendulum right here. So this is a fixed surface. So this is a pendulum. This is mass. So initially, if we displace the pendulum, so it's making an angle, theta. So the length is L. So, right? So now the pendulum will have a force, mg, down here. But also, it will be decomposed into some vector around here, which is just mg sine theta. So I need to prove that this also undergoes simple harmonic motion, which is the second order differential we see previously for the spring. So I assume we have a try at it. So first we can realize that torque is just equal to the moment inertia times angular acceleration, but it's also equal to force times the radius. So there's going to be a force, mg sine theta, down here. So negative mg sine theta times r, which is just length here, equals to I alpha. Now we know I is just the moment inertia, and moment inertia for a rod that's rotating around one fixed end is just going to be mr squared, or ml squared in this case. And alpha is just angular acceleration, which is just the second derivative of theta. So you can write it in terms of that. So we get negative mg sine theta L is just going to be equal to ml squared, and then d squared theta dt squared. Now we can cancel out m here and m here, and one multiple of L here and one multiple of L here. And now we get g sine theta equals to L d squared theta over dt squared. Now we know for small angles of sine theta is approximately just equal to theta for theta that's like smaller than 10 degrees. So we can write it as theta, so we get g theta equal to L d squared theta over dt squared. Don't forget a negative, oops. So we put this on the other side, we get, and then we divide both sides by L, right? So we get d squared theta dt squared plus L g over L theta equal to 0. So you see this indeed is the equation for simple harmonic motion. So we know the pendulum does indeed undergo simple harmonic motion if it's only displaced by a little bit. So solving this, we can get theta as a function of time is equal to theta naught, or the original displacement, or the maximum displacement. It's like amplitude in a way. So times by sine omega t plus phi. I could do the same thing to analyze the period of this pendulum. We know that omega equal to 2 pi over t. I've already seen this before, so I'm just going to skip out the medium step. So we get time, which is equal to 2 pi, and then L over g. And this is the end of the video. Thanks.